Hello everyone, in this video I am going to be discussing about the organic waste anaerobic fermentation, a sustainable approach. Understanding the anaerobic digestion process. There are three under this: hydrolysis, acidogenesis and methanogenesis. Hydrolysis involves complex organic molecules are broken down into simpler compounds by enzymes. This step involves the breakdown of carbohydrates, protein and fats into sugar, amino acids and fatty acids. Then we have acidogenesis. Organic acids such as acetic acid are produced by bacteria. This stage involves the conversion of sugars and amino acids into volatile fatty acids, alcohols, hydrogen and carbon dioxide. Then methanogenesis: methane producing bacteria convert acetate and hydrogen into methane and carbon dioxide. This final stage results in the production of biogas, primarily consisting of methane and carbon dioxide. Then we have benefits of anaerobic fermentation. So the first one is renewable. Biogas produced during anaerobic fermentation is a valuable source of renewable energy. This biogas can be used to generate electricity, produce heat, or be upgraded to biomethane for use as vehicle fuel. Then we have waste reduction. Organic waste is converted into biogas and digested, reducing the amount of waste going to landfills. This process helps in managing municipal, agricultural and industrial organic waste effectively. Then we have nutrient recovery. Digestate is rich in nutrients that can be used as fertilizer, promoting sustainable agriculture. Digestate contains nitrogen, phosphorus, and potassium essential for plant growth. Then we have reduced greenhouse gas emissions. Anaerobic fermentation helps mitigate climate change by reducing methane emissions from landfills. Capturing methane during the anaerobic digestion process prevents its release into the atmosphere. Moving on to feedstock preparation and pre-treatment. Under this we have size reduction. Organic waste is shredded or ground to increase the surface area for microbial activity. Here we reduce the particle size, which enhances the efficiency of the hydrolysis process by providing more accessible surface for enzymatic action. Then we have moisture adjustment. The moisture content of the feedstock is adjusted to optimize levels of anaerobic digestion. The ideal moisture content is typically between 50 to 70%, ensuring a conducive environment for microbial activity. Then pre-treatment. Thermal, chemical or mechanical pre-treatment methods can enhance efficiency. Pre-treatment helps in breaking down complex organic material into simpler forms, making them more accessible to anaerobic microorganisms. Now let's move on to reactor design and operation. So we have three types of reactor design: batch reactor, continuous reactor and stirred reactor. So the batch reactor, the feedstock is loaded into the reactor and digested for a fixed period. Once the digestion process is complete, the reactor is emptied and a new batch is loaded. Then we have continuous reactor. Feedstock is continuously fed into the reactor and digested material is continuously withdrawn. This type of reactor allows for a steady state of operation and continuous biogas digestion production. Then we have stirred tank reactor. This reactor is continuously agitated to ensure uniform mixing of the feedstock. Mechanical or hydraulic agitation can be used to maintain homogeneity and prevent setting of solids. Let's talk about biogas production and utilization. So composition. We have methane, which is a primary component of biogas, making of 50 to 70%. Then carbon dioxide. The carbon dioxide constitutes 25 to 50% of the biogas, and then there are other gases which include small amounts of hydrogen sulfide, ammonia, and other trace gases. These gases need to be removed or reduced for certain applications to prevent corrosion and meet quality standards. Then under utilization we have electricity generation. Biogas can be used to generate electricity using internal combustion engines, gas turbines, or fuel cells. Then heat production. Biogas can be burned directly in boilers to produce heat. And fuel for vehicles. Biogas can be upgraded to biomethane and can be used as a biofuel. Let's talk about the digestate management and utilization. Under that we have three. The first one is solid digestate. Now solid digestate is a nutrient rich material that is used as a fertilizer for growing crops in agriculture. Then we have liquid digestate. This is used in irrigation or further processed for nutrient recovery. The third one that we have is beneficial uses. Beneficial uses of the digestate. Digestate can be composed or it can be used in biogas production. Let's talk about the environment impact and sustainability. Now, under this, we have reduced waste, renewable energy, soil improvement, and climate change mitigation. So, in reduced waste, anaerobic digestion reduces landfill waste, minimizing the environmental impact on the environment. Then we have renewable energy. Biogas production provides a sustainable energy source, reducing reliance on fossil fuels. Soil improvement. Digestate enriches soil fertility, promoting sustainable agriculture practices. Then climate change mitigation. Anaerobic fermentation reduces greenhouse emissions from the waste. Now we have reduction in greenhouse gases. This helps, anaerobic fermentation helps in reducing the waste uh, and converting agricultural residues, food waste, and other organic materials into valuable products like biogas and digestate. Let's now move on to the challenges and limitation. The first one is high initial investment. To setting up anaerobic digestion facilities requires significant capital allocation. Costs include infrastructure, equipment, and technology for biogas production and upgrading. Then we have operational complexity also. Anaerobic digestion systems require careful management and technical expertise. For example, in maintaining optimal conditions for microbial activity, such as temperature, pH, and nutrient balance. Then we have feedstock variability. Inconsistent quality and availability of feedstock can affect the biogas production. Variation in organic waste composition, moisture content, and contamination level. Now moving on to the future trends and innovation. We have integrated biorefineries where combining anaerobic digestion with other bioprocessing technologies to maximize resource recovery. Then biogas upgrading, technologies for upgrading biogas to biomethane for transportation fuel. Then we have advanced pre-treatment, developing innovative pre-treatment methods to enhance digestion efficiency. Then circular economy, integrating anaerobic digestion into the circular economy for waste valorization. Then we have different biorefinery concepts that can be used as future trend and innovation. Now with that, I come to the end of the video. Thank you for watching the video.